Okay, good afternoon. This is Schweitzer, and we're going to run through a whole bunch of types of calculations, and they're all going to kind of circle around the same sort of idea here. So we'll just start working our way through these things. This slide here is for you. It should be in your workbook or your packet of notes that you can use this to kind of put some notes on from the next few slides. So as we move along here, these are some concepts that we're going to sort of be looking at here: spontaneous, non-spontaneous, exergonic, endergonic. So you can see where you want to add your own notes. Okay, so in this situation here, so is a reaction spontaneous? What does it mean? What does it really mean for a reaction to actually be spontaneous? What it means is that it flows from reactants to products all by itself. You don't have to add energy. So when you have reactions going towards products and you need to add energy into this thing in order to drive it that way, well then if you don't add the energy, then you don't go to the products. And conversely, if you're already at products, then you should be able to flow back towards reactants, and then that energy can begin released all by itself. So anytime energy is contained inside of the substance and it simply just needs to release it, well then you don't have to do anything and it can happen all by itself. It's kind of like having money in your pocket, going to the mall, or nowadays logging on to Amazon and you got money in your account. It's just a matter of time before that money gets spent. Okay, and it happens all by itself. If you need to put energy in, well then you need to drive that reaction. This energy is driving the reaction in that direction, that reaction in that direction, and won't happen until energy is available. So if you want to buy something and you don't have the money, then you got to wait until that money shows up and then you can have it. But with that being said, it's not that it can't happen, you just need the money first. So let's look at an example. Stickman, okay? He's sitting here and he jumps up, okay? Well, where did this energy come from? Now he has got some height, he's got potential energy, and then he's got some obviously moving, he's got kinetic energy. He jumps for joy. So where did the energy come from? Okay? Well, it came from inside this guy's cells. He already has the energy, okay? And he has it. He just uses it up. So in this situation, again, as he comes back down, okay, now answer the question. The Stickman already had it in the form of bond energy. Stickman system, okay, he's a system, lost energy overall, del G is negative. So he had the energy, and now he doesn't have the energy. So technically, this guy here has more energy than the same guy over here. Keep in mind, this is like a chemical reaction. This could be X going to, X. This is before, this is after, okay? Plus energy. He just has less energy here than he does here. Same guy though, right? So what happens to the temperature of the room? Well, technically the temperature should go up because he's getting rid of energy, spending energy, and eventually energy dissipates to the area, and there you go. Again, an example, you have a bunch of kids are playing in a gym. What happens to the temperature of the gym? Where did that energy come from? It came from inside the kids, right? So with that being said, keep in mind, a negative delta G, we call that Gibbs free energy. That's a sort of made up by people, Gibbs, apparently. Free energy. It wants to know, do you have the energy inside of you to use? And if you do, and you can lose it, then you are spontaneous, which means that the reaction is just going to run without having any effort. So effort, I mean adding any extra energy. So anytime something is negative, it means it literally is going to flow from what's on the left side to what's on the right hand side. We call this the reactants, and we call this the products. Okay. Again, this analogy, negative G, means it's running. It's happening all by itself. Stickman gave heat energy away from surroundings, that would be exothermic. Okay. All right, so again, reactions going to products. System before, system after. A couple things you want to know about delta G. This system reactions will proceed to products with no added energy. So a negative delta G indicates something that is spontaneous. And eventually we have to have a loss of energy. If we go before gaining energy, okay, that means positive delta G. This is a non-spontaneous process. Okay. So reactants will proceed to products with no added energy. That's this guy right here. System will overall lose energy to surroundings. So it's going to lose energy to the surroundings. The surroundings therefore must be gaining extra energy. Just the opposite for a positive delta G. This one, if this energy is not available, then it's not going to happen until it's available. All right. Basic summary. All right, so what can we say about delta G prime? Keep in mind that little prime symbol there means at STP. Okay. What do we know about all this stuff? This is kind of just delta G in general. Okay. Delta G prime means when you have STP. That's 25 degrees Celsius in this area of chemistry, by the way, not 0. It means 1 molar concentrations of both reactants and products. I have them located here. It also means 1 atmospheric pressure. Okay, keep in mind that no matter what you do with this, everything is 1 molar, regardless of your chemical reaction. When you plug in your algorithm, products of reactants, regardless of the reaction, x squared, I should say 2x goes to y. It doesn't matter, okay, if it's 1 over 1 squared, it's always 1. So Q at STP, I tend to call this thing STP 0, is always 1. So now that the Q is 1. Okay. So delta G, in this case, is kind of like at STP, is kind of a pointer sign. If delta G is negative, okay, that means that you have to go to the right, which was just mentioned. Delta G is always at the end, where K is located, is approaching 0. Delta G, it's not prime anymore because it's only prime when it's at 1 molar or 1 molar. When we start losing reactant, gaining product, we're no longer at 1 molar anymore. So we're not no prime anymore. Okay, so you always want to keep in mind as we go from prime, and no matter what, as delta G moves spontaneously, it approaches 0. Okay, this guy goes to 0. It might be getting bigger to go to 0. If you happen to be over here, it will get bigger, okay, or smaller or bigger, whichever one. It's approaching 0, and that's how you want to answer that. You don't, because there's a lot of negatives involved here, so you don't necessarily want to say it's getting bigger or smaller. Say it's approaching 0. Okay? So Q becomes K, Q will become K, and delta G will go to 0. In this case, Q is 1, K, Q was smaller than K, and Q got bigger to approach K. So on the right hand side here, if K is greater than 1, which is what it is right here, then we know we're going to be product favored. And that's kind of a big picture kind of idea here. Okay. Let's see if I forgot anything. I think we're pretty good there. All right, so what does it mean if reaction has a positive delta G? Now, in this case, if you say positive delta G, all that means is that literally, the positive means that if we let this thing go, reactants, products, that we will flow to the left to get to equilibrium or ending. Okay, that's what it means. It's a little different if you say positive delta G prime. Okay, that means you will starting here. You have to go this way to get to the end point of K. Therefore, K must be less than 1. So if del G is prime, then the K value must be less than 1. But if you don't have the prime symbol on there, all it means is you're going to the left. So you could be located right here, delta G could be here, and you're going to end right here. Okay, we don't know a reference point of where we're starting versus where we're ending, but delta G prime does mean we're starting here. If delta G equals 0, that just means your Q equals your K and you're at the end point. Okay, it means that your the reaction going forward is no more benefited than the reverse reaction. You're kind of at a stalemate. All right, once again, what does delta G, negative delta G means? It means that to get to your K value, if delta G is negative, delta G prime is negative, all it means is that we're moving to the right. Delta G negative just means we have to go to the right. We don't know where we are. We could be located right here, and we could be ending right here. All right, delta, this could be our K value. Going to go that way. We're going to go to the right. Does it mean you're guaranteed to be product favored? No. This means you're moving to the right. If your delta G prime is negative, that's different. It means you're starting with 1 molar, and therefore your Q equals 1. And therefore, as you go to the right, you're always going to be product favored. Because if you have equal amounts of both and you tip to the right, well, then you have to lose this guy and gain this guy, and you're going to be over here. This means that your K is greater than 1 because you started with Q equaling 1. All right, so that's kind of a big picture idea, and there's lots of little multiple choice questions in and around this sort of idea. All right. What are the factors affecting delta G, Gibbs free energy? Are we going to gain or lose energy? Well, this is the main formula that we have here, and it's on your laminated sheet. So there are basically 3 factors. We have delta H, which we call enthalpy. That's like your heat, your hotness. We have entropy, which is brand new here, and we're going to kind of skirt around the actual details of it a little bit here. We'll introduce the details of it in the next piece. And we have temperature. Okay, keep in mind a negative delta G means that the system is losing heat energy, negative Q. So we're losing energy. Of course, we know if you have the energy, or you have like money, and you just have to lose it, well then you're fine. Okay, you can lose it whenever you want. This is a bigger piece of the pie, by the way. All right. People didn't know about this section here for a long, long time because it's smaller. And we'll talk more about that. And people thought that these two were the only things that were there. But there's one more little aspect of it called entropy, which we'll be getting into in a little bit. But again, smaller piece of the pie. But for a complete picture, we have to include it. All right, let's move into a little more details of this thing. Now, on this slide, on this presentation, we'll be looking at this formula a lot, but we won't necessarily be calculating with it. The next presentation we'll look at calculations and all of it, but we'll look at just estimations and mental math using this particular formula. So keep that one in close by. All right, so what is entropy? Just a quick little heads up on entropy. Okay, well, it's symbolized by a letter S for entropy. It's energy per joules per Kelvin is its unit. I tend to think of it as a kind of a form of energy. And we'll see why that is in a minute as we move along. Okay? Notice its units are energy per degree Kelvin, so it is kind of like a form of energy. Disorder or energy tied up in order. So they often think of it as entropy as the amount of disorder. And I don't necessarily like that as much. I think of it as the energy tied up in order. Like in order to make order, you have to have energy to order something. So we're skirting along the edge of what this really is. It's often, again, the amount of movement. So I choose the definition that I need to help me at that time when I'm using it. for an overall idea. Again, so what does it mean? A system goes from X to this. It is a positive entropy change. That means one of these things, that the overall system could have gained from here to here, gained movement. That might be one of the most common things that you might think of it. Or you could say that it gained disorder. And we'll learn a little more about that as we go. Disorder is kind of like movement. Okay, to lose entropy, that means from start to finish. Okay, the change, that's that change right here, is this subtraction between the two, is negative. That means you lost disorder, or you gained order. To gain order would mean maybe you have less movement. Okay. So a little bit about entropy, kind of a form of energy. All right. Major takeaway. Entropy is the energy type in order, disorder. We got that. It takes energy to create order. This is not free. That's an interesting one. So if we're going from substance X to substance X, and let's say this substance is gaining order, so it's got a negative delta S, okay? So that means I lost disorder or I gained order. This is not free, okay? So you would need to add energy in order to do that, okay? Just the opposite, however, if you go from X to X and you have a positive delta S, this is going to go from here to here, is going to gain disorder or lose order. That's free. That doesn't cost anything. That would give away energy in the process. Okay, that unravels. So think of it like your bedroom. Your bedroom gets dirty all by itself. That's this process. You don't have to add energy. It just happens. And to clean your room requires energy and will not happen unless you put energy in. You put energy in and then it unravels again. You put energy back into it and it unravels again. Just that's life. In nature, processes that create disorder happen spontaneously. Means you don't have to add any energy to get it to run. It just happens. In nature, processes that lose or create order need to be fed all the time. They're hungry, right? And will not happen unless the energy is provided. Our wonderful sun provides lots of energy to Earth, and really photosynthesis and light energy feeds the whole Earth and creates lots of order, which is then, of course, just disorders. All right, so what do the signs mean? Okay, again, there's lots of signs here. We got to keep in mind that you don't want to memorize things. So if you're memorizing this, oh man, you really got to get away from that. System versus surroundings. Keep in mind that if you're losing energy, that happens kind of all by itself, okay, and would be considered spontaneous. Keep in mind, we're always thinking in terms, we are the system. All right, the reaction thinks of it as a system. You might be out here, okay, but the chemistry thinks of it in terms of the system. So the beaker is the system. You are on the outside. So enthalpy, negative delta H. That's because the system is losing energy to you. So you get hot. So this is negative, but that's a spontaneous process. Remember, anytime we have energy exit the system, that's spontaneous. The wood from campfire contains all the energy already. Just needs to lose it. Therefore, when it burns, you feel hot. And it burns all by itself. You don't have to do anything. It just goes. You need to get it started, but once it's going, it keeps going. A positive delta H is one where stuff enters the system. And therefore, you might lose energy, you'd feel cold. And this is, of course, non-spontaneous. And this is an endothermic. Got a special name for it. And this is, of course, exothermic. So endothermic reactions are non-spontaneous. They don't typically happen by themselves. So you'll notice that in our everyday environment, there's a lot more exothermic reactions than there are endothermic ones, because they're a little rarer. entropy. Okay, if a system has a positive delta S, that means the system is gaining disorder. Okay, a negative delta S means that the system is losing disorder. Okay, now, in this again, it's referenced in terms of the system. Which one happens? Gain disorder, or you are losing order. Okay, gaining order. And you can think of it as movement as well. So to gain disorder happens all by itself. Okay, so this is going to be a spontaneous process, and this one is non-spontaneous. Keep in mind, gaining order is not free. You need to add energy to order something, and then it unravels all by itself. This one unravels all by itself, no problem. Gaining order or losing disorder is not free. All right, Gibs. The Gibs is these two guys included, combined. You'll notice that our formula is delta G equals delta H minus temperature times delta S. This is one factor right here. Temperature is a factor, but it only affects the entropy. Either way, this factor and this factor are what come together to form delta G. Keep in mind, negative delta G means, now these might be factors affecting spontaneous. This is a factor, but it isn't the only thing that affects delta G. This also has an effect. So with that being said, these are just inputs, like pieces of the pie. Okay, this is the net result. This is like what actually is going to happen. Delta G means this reaction is running. When I mean it's running, it means it's flowing from reactants to products. And there's going to be a net loss of energy. I don't know if it's going to be in terms of order or if it's in terms of heat, but net loss of energy. Okay. If I have a positive delta G, doesn't mean it can't run. It means it will only run if energy is added. Okay, so it's not running if the energy is not available. Not running as of right now. We'll need to add energy. You know, cooking is a big example of an endothermic process. It only runs when you add energy to it, and you need to keep feeding it. You need to feed this guy right here, or it will not run. It's like pushing a ball up a hill. Okay, you have a hill here, and you're going to push a ball up the hill. Pushing the ball up the hill is a positive delta G. That means that it will only go up as long as you're adding energy. You stop adding energy, the ball doesn't go any farther. It even roll down. But if you have a ball at the top of a hill, it already contains the energy. This is a negative delta G, meaning that all it's got to do is give a little nudge and it just rolls all down by itself. Eventually, they end up in the same spot where delta G would equal 0 because there's no more thing happening anymore. All right, so keep in mind, positive must feed energy. Of course, at this point, if the ball gets up to the top, this was, of course, a positive delta G because we needed to add energy. From here to here, negative delta G, we lost energy. The ball has less energy, has less potential energy. All right. So again, a couple things we're looking at here. Two different factors affecting delta G. And I got to piece through the math on this. We'll do some more on this as we come along down the line, but if we have a positive delta G, delta S, which is a spontaneous factor here, and temperature, of course, this has to be in Kelvin, means this whole factor mathematically with a negative here, negative into positive equals negative. This whole factor here, this whole factor is negative. A negative plus a negative means this has to be negative. That's a really important thought process there. If this is negative and this is positive, well, negative times a negative is positive. Okay, positive plus a positive is always positive. Right? This guy is always cannot be. That means won't run. This means it just means you need to add energy to get this thing to run. Okay. So that's kind of how we use our signs to really manipulate this equation and see what we can find out about it. All right, indicate the possible signs of delta G. All right, let's try this out once. What happens to delta G as the temperature goes up? Okay, so in this situation, I like to come up with a new sign for this factor. Negative times a negative is a positive. Positive plus a positive must be positive. This is non-spontaneous then. I have a negative times a negative is positive. Hold on a second here. So, okay, that's the top one here. So, negative times a negative means this whole thing here is positive. Positive plus a negative, I don't know. I got a negative and a positive. It really depends on how big the temperature is. So if the temperature goes up, remember, you cannot have a negative temperature because we're in Kelvin. If the temperature goes up, then my positive goes up. And delta G moves towards being positive or non-spontaneous. If delta G goes, if it goes down, just the opposite occurs. Okay, then this factor gets smaller, and the negative here can start being more prevalent. Okay, positive times negative means this whole factor is negative. So it means this factor is pushing in the spontaneous direction. Just like before, this factor was pushing in the non-spontaneous direction. So positive, this is going to be positive is negative. Okay, negative and positive. Now again, they're conflicting here. Who wins out? All depends on temperature. Now if I increase my temperature, then this factor, which is pushing in the negative direction, is going to become bigger. And delta G will move to become negative, or maybe towards become spontaneous. We don't know delta G. Temperature plays a role. Temperature plays a role. Positive times a negative means this whole factor is negative. It's pushing in the spontaneous direction. Okay. But this delta G is also negative. So both factors are pushing in the spontaneous direction. So mathematically, or whatever, this has to be negative, and it will be spontaneous, regardless of what temperature. Temperature does not matter. Here, temperature does not matter. So these two here, we could alter the temperature and eventually come to, can I spell alter the temperature, where at some point delta G becomes negative and the reaction runs towards products all by itself. Okay? Or this one, top one, no matter what the temperature is, temperature doesn't matter. It's never going to run by itself. It will always need to be fed. The bottom one here, temperature does not matter. Okay? It will always run, regardless of the temperature. There are some examples you might see, like say ice melting. Does ice always melt all by itself? Well, no, it depends on the temperature. Does wood burn regardless of temperature? Probably, yeah. Even on cold days it burns. Interesting concept there. All right. Here's just our general notes information on temperature. Okay, so if that did make sense, take a look here for clarification. All right, can you predict the signs of these? What is the sign of delta G if we have a negative delta H and a negative delta S? Okay, take a look at this again. Try it on your own. Negative times negative is positive. This is negative, so negative positive, we don't know. Depends on temperature. What happens to delta G? What happens to delta G if we have a negative delta H and a negative S and we raise the temperature? So that's the same thing we just did here, and I raise my temperature. That means my positive will become bigger, and delta G would be moving towards becoming more positive. I'm not saying it's going to get there, or it's there already, but it'd be moving more towards positive or moving more towards non-spontaneous. So it'd be less likely to run all by itself. Student hypothesis: if a reaction is proceeding and is exothermic, it must have a positive delta S just for nullify. Okay, so it doesn't really make a whole lot of sense. I mean, those two are completely disconnected. So if we have a positive, if a reaction is proceeding, here we go. If a reaction is proceeding, now that's a little key word here that I was going to tell you. That means it's going, it's running. Delta G must be negative. It's running. And delta H is negative. All right, let's see what we got here. So I might give myself a little room here. Let's rewrite down what we got. All right, so this is negative and this is negative. It must have a positive delta S. Well, first of all, it doesn't have to have anything. All you need is one of these guys pointing towards spontaneous, and then this guy can vary. So if this is positive, then the negative and positive and negative is negative, and it will definitely run. So this is nullified because this thing could be negative. Negative and negative is positive. But if the temperature is very small, so a positive entropy and a low temperature would work and still become, and this could still be the negative. That's the big idea we want to come out of this with. All right, and we'll end our overall Gibbs idea here in entropy, and we'll be doing much more calculations on the next slide. Thank you.